Hello students, welcome to another physics lesson. I hope all of you are in good health. I know it is not easy to stay at home for such a long time, but we must be very wise in this difficult time so that this pandemic does not get worse and our activity can return to normal condition as soon as possible. Keep your spirit high and take time to pray for those who has to be on the front line in this war against the virus. Now, let's continue to our lesson. Today, we will learn about microscope. The simplest compound microscope is constructed from two convex lenses as shown schematically in the figure. As you can see here, there are two convex lenses. This is the first one, and this is the second one. The first lens is called the objective lens and has typical magnification values from 5 times to 100 times. In standard microscopes, the objectives are mounted such that when you switch between objectives, the sample remains in focus. Standard microscopes have 3 different objective lenses. Each lens has different value of magnification. Objectives arranged in this way are described as parfocal. What is the meaning of parfocal? Parfocal means having sets of objectives which allow you to adjust each objective lens so that it will remain in relative focus with the other objective lenses on the microscope when switching from one magnification to the next. The object for objective lens is always placed between the FO and 2FO. 2FO means 2 times FO. So the distance from 2FO to the lens equals to 2 times the distance from FO to the lens, where FO is the focal point of the objective lens. So the object must be placed around here to form a real and enlarged image. Now, how does a microscope form an image? The purpose of a microscope is to magnify small objects, and both lenses contribute to the final magnification. Additionally, the final enlarged image is produced in a location far enough from the observer to be easily viewed, since the eye cannot focus on objects or images that are too close. This is the object. It is placed slightly farther away from the objective lens than its focal length, FO, producing the first image that is larger than the object. This is the first image. The first image is the object for the second lens eyepiece. So the object for the eyepiece is the first image formed by the objective lens. The eyepiece is intentionally located so that it can further magnify the image. The eyepiece is placed so that the first image is closer to it than its focal length, FE. Thus, the eyepiece acts as a magnifying glass, and the final image is made even larger. This is the final image. you can compare. This is the object, and this is the final image. You can see there that the final image is much more larger than the object. The final image remains inverted, but it is farther from the observer, making it easy to view. The eye is most relaxed when viewing distant objects and normally cannot focus closer than 25 cm. Perhaps you still remember that it is impossible for a single lens to form a virtual and inverted image. A single lens produces either virtual and upright image or real and inverted image. But microscopes use two thin convex lenses. In the arrangement of two thin lenses, the image from the first lens, this is the image from the first lens, where the first lens is the objective lens, becomes the object for the second lens. The second lens is the eyepiece. The image formed by the objective lens, which is already inverted, as you can see here, the image from the objective lens is inverted to the real object, becomes the object for the eyepiece. In this condition, the eyepiece considers the inverted image as an upright object. So, the final image for microscope is virtual, inverted, and enlarged. Since based on the eyepiece, this is the object, and the eyepiece said that this is the upright object. So, according to the eyepiece, this is also upright. But if we compare the final image to the initial object, it is inverted. Since each lens produces a magnification that multiplies the height of the image, it is apparent that the overall magnification, M, is the product of the individual magnifications. So M equals to MO times ME, where MO is the magnification of the objective lens, while ME is the magnification of the eyepiece. The magnification of objective lens is the same as the linear magnification. So MO equals to SIOB over SOOB, where SIOB is the distance from the first image to the objective lens, and SOOB is the distance from the object to the objective lens. The eyepiece, or the ocular, behaves as a magnifying glass. So we can divide the magnification of the eyepiece into maximum magnification for eye with maximum accommodation. The formula to calculate the maximum magnification refers to the formula of the angular magnification of the magnifying glass for eye with maximum accommodation. So it is equal to PP over FE plus 1. While for the minimum magnification for eye without accommodation, the angular magnification equals to PP over FE. PP is the near point of the observer, and FE is the focal length of the eyepiece. The length of the microscope is defined as the distance between the objective lens and the eyepiece. So from the figure, this is the center of the objective lens, and this is the center of the eyepiece. The length of the microscope is defined as the distance between the objective lens and the eyepiece. So this is L. L stands for the length of microscope. So here from the figure, we can see that L equals to SIOB plus SOE, where SIOB is the distance from the first image to the objective lens. From here, this is the first image to the objective lens. And SOE is the distance from the first image to the eyepiece. Remember, the first image becomes the object for the eyepiece. That's why we give the symbol SOE. SO stands for the distance from the object to the lens, and E stands for the eyepiece. Let's do the work example. Calculate the minimum and maximum magnification of an object placed 6.2 mm from a compound microscope that has a 6 mm focal length objective and a 50 mm focal length eyepiece. The minimum magnification is the total magnification for observation without accommodation, and the maximum magnification is the total magnification for observation with maximum accommodation. Remember, total magnification is the product of the magnification of the objective lens and the magnification of the eyepiece. So now we will start the calculation from the magnification of the objective lens. From the problem, we know that the distance between the object and the objective lens, or SOOB, equals to 6.2 mm. And the focal length of the objective lens, or FO, equals to 6 mm. The magnification of the objective lens is a linear magnification. Therefore, to calculate the magnification of the objective lens, we have to know the distance of the first image from the objective lens. So now, let's calculate the SI of the objective lens using the general equation 1 over SOOB plus 1 over SIOB equals to 1 over FO. This gives us 1 over 6.2 plus 1 over SIOB equals to 1 over 6. So 1 over SIOB equals to 1 over 6 minus 1 over 6.2. The equation will become 3.1 minus 3 over 18.6. This equals to 0.1 over 18.6. So, SIOB equals to 18.6 over 0.1, or 186 millimeter. Because the magnification of the objective lens equals to the linear magnification, So we will use the equation MO equals to SIOB over SOOB. SIOB equals to 186 over SOOB is 6.2. This equals to 30 times. So the magnification of the objective lens equals to 30 times. Now let's calculate the minimum and the maximum magnification of the microscope. Minimum magnification is caused by the observation without accommodation. And the maximum magnification is caused by the observation with maximum accommodation. For minimum magnification and for maximum magnification, the value of the objective magnification will not change, because the magnification of the objective lens does not affected by the condition of without accommodation and maximum accommodation. So remember, the value of the magnification of the objective lens will be equal for both minimum magnification and maximum magnification. So now let's just write down the value of MO. For minimum magnification is 30 times, and for the maximum magnification, the value of MO is also 30 times. From the problem, we have that the focal length of the eyepiece, or FE, equals to 50 millimeter. We will change or convert the unit into centimeter, which gives us 5 centimeter. Now we can calculate the magnification of the eyepiece. Minimum magnification is the magnification for observation without accommodation. So, the correct equation of the ME for the condition of without accommodation equals to PP over FE. The problem does not state about the condition of the person's eye. So let's consider that the person has normal eyes. Therefore, we will consider that the PP of the person, or the near point of the person, equals to 25 centimeter. FE is 5 centimeter, so we have ME equals to 5 times for the condition of without accommodation. So the minimum magnification is the product of MO and ME. This equals to MO times ME equals to MO is 30, the ME is 5. We will have 150 times. Now for the maximum magnification. Maximum magnification is the magnification for the condition of maximum accommodation. So the correct equation for the ME is PP over FE plus 1. PP is 25 centimeter over FE 5 centimeter plus 1. This equals to 6 times. Now, the maximum magnification equals to MO times ME. The MO is the same as the minimum magnification, which is 30 times, but the ME is 6 times. So this equals to 180 times. So the final answer for maximum magnification is 180 times, and for the minimum magnification is 150 times. That's the answer for our work example. This is the end for our lesson today. I will not give you any assignment for today, but in the next week, I will give you some work example about microscope, and also you will receive some assignment also about microscope. So that's it for today. See you on Monday. Have a nice weekend. Bye.